Okay, this is Chapter 6, Lesson 3, and tonight we're going to focus on calorimetry. We're going to talk about what calorimetry is, we're going to define some important terminology, and then we're going to talk about the difference between constant volume and constant pressure calorimetry. So calorimetry in general is the measure of heat flow, and we can calculate delta H or delta E from this. The first thing that we're going to talk about is heat capacity, and that's the amount of heat required to raise the temperature of a body by 1 degree Kelvin. It's also dependent on the nature and amount of the material in an object. Next is molar heat capacity, and this is the heat capacity of 1 mole of a substance. So in this type of problem, we might be given the grams of a substance, and we might find the heat capacity for that number of grams and then use stoichiometry to determine it for 1 mole. Also, I'm just going to abbreviate this MHC just because I don't have enough room to write it out. Molar heat capacity, it is equal to the quantity of heat this is usually represented in joules or kilojoules, divided by the moles of substance times delta T, change in temperature. And specific heat capacity is the heat required to raise 1 gram of a substance by 1 degree. And for this one, we're usually using Q equals MC delta T, which you're familiar with from Regents Chem. And your specific heat capacity, your units for C could be in joules per gram dot Kelvin or joules per gram dot Celsius. Having trouble with the eraser there. All right. So usually in a calorimetry problem, you're either finding specific heat or you have to be given the specific heat for a certain substance. If it were a test question and you had to find something else in the problem, you would be supplied with the specific heat capacity in the problem. Just pointing out the difference in specific heat for water that is in the liquid state versus water in the solid state. So what this is showing us is that you know that when something goes from a solid to a liquid, it absorbs energy, and it takes less energy per gram to raise 1 gram of ice 1 degree Celsius than it does for a liquid. And this should make sense because has to do with particle position. Particles in a solid are closer together, therefore they can transfer their energy to particles that are closer to them than particles that are further apart. So here's our first example. A swimming pool 10 meters by 4 meters is filled to a depth of 3 meters with water at 20.2 degrees Celsius. How much energy is required to raise the water temperature to 30 degrees? So first of all, we know that we're using a Q equals MC delta T. And we are trying to find energy, so we are finding Q. We know the specific heat capacity of water is equal to 4.18, so we're writing down what we know, joules per gram dot Celsius. We know that our delta T is equal to 30 degrees because it was raised. Now the only thing that we're missing is the mass. However, we are given the dimensions of the swimming pool, so we know that volume is equal to length times width times height. So in this case, this is going to give us a volume of 120 meters cubed. We now need to change that to grams. So 120 meters cubed, we know that 1 meter cubed is equal to 100 centimeters cubed. Please remember to cube this. A lot of you didn't do that on the dimensional analysis lab. And we know that 1 centimeter cubed is equal to 1 milliliter. And we also know that 1 milliliter is equal to 1 gram. So all of our units cancel. And when we do the math on this, we come out with a mass of 1.2 times 10 to the 8th. 1.2. Getting into the red zone over here. 1.2 times 10 to the 8th grams. So that is our mass. So using Q equals MC delta T, we have 1.2 times 10 to the 8th grams times 4.18 joules per gram dot Celsius times 30 Celsius. And our Celsius cancels and our grams cancel, and we're left with joules. 4.9 times 10 to the 9th joules. And that is our answer. All right, looking at a second problem. How much energy is required to raise the temperature of an 8.5 times 10 to the second gram block of aluminum from 22.8 to 94.6? So the first thing that I notice when I'm looking at this problem is I'm dealing with aluminum, so I know that I'm going to need the specific heat capacity of aluminum, which on the previous, so this is for AL, was equal to 0.89 joules per gram dot Celsius. And we know that our delta T is 94.6 minus 22.8, which is going to give us 71.8 degrees Celsius. So this one's a simple plug and chug. My Q is going to be 8.5 times 10 to the second times 0.89. I'm going to leave my units out for space here. I'll cancel them on the side. 71.8. Okay, so my Celsius cancels and my grams cancel, and I'm going to be left with joules. And that's going to be 54,316.7. 54,316.7 joules. That's the first part of the question. Second part of the question says, what is the molar heat capacity of aluminum? So we know that the molar heat capacity is 0.89, and that's joules per gram dot Celsius. So we need this for a mole, so we know that 1 mole of aluminum is equal to approximately 27 grams. So our grams are going to cancel, and this is going to give us joules per mole, which is 24.03 joules per mole dot Celsius. Next problem, Ti metal is used as a structural material in many high-tech applications, including jet engines. What is the specific heat of Ti if it takes 89.7 kilojoules to raise a 33 kilogram block by 5.2 degrees Celsius? So this is the first part, and then they want the molar heat capacity. All right. So a little spin on the Q equals mc delta T formula. We are now finding the C. Therefore, C is going to be equal to Q divided by m delta T. Simple rearrangement of an algebraic equation. Another thing that I notice is that C is usually reported in joules per gram per degree Celsius, and I've got units in kilojoules and kilograms. So I have to make some adjustments there. So I've got 89.7 kilojoules, and we know that 1 kilojoule is 1,000 joules. So that's going to give me 89,700 joules. The second thing, 33 kilograms, so 33 kilograms, and I know that 1 kilogram is 1,000 grams. So that is 33,000 grams. So now I'm pretty much set. My C is going to equal my Q, which is 89,700 joules, divided by M, 33,000 grams, times delta T, which we know is 5.2 degrees Celsius. And when I do the math on all that, I get 0.523 joules per gram dot Celsius. So that's the first half. It's problem 1. And then in problem 2, they want to know what the molar heat capacity is. Well, we just did this in the last problem. We have 0.523 joules per gram dot Celsius, and we want to know for 1 mole. 1 mole of Ti has a gram formula mass of 47.6 grams. This cancels, and I'm left with 24.9 joules per gram dot Celsius. Okay, in yet another example, large beds of rocks are used in some solar heated homes to store heat. Calculate the quantity of heat absorbed by 50 kilograms of rocks if their temperature increases 12 degrees. and the specific heat of the rocks is 0.82. So I am finding my heat, which is Q. I notice that I have a disagreement of units. I've got kilograms and joules per gram. So I think that most of you know, I did show it on the last one, 50 kilograms would be the same as 50,000 grams. Okay? So my Q is going to be equal to 50,000 grams times 0.82 joules per gram dot Kelvin. And remember that Kelvin and Celsius, the change, they're still equivalent to 1, so I can just simply make this 12 degrees Kelvin. My units will cancel. And when I do the math, I get 492,000 joules. This could also be 4.92 kilojoules, depending on how they asked you to report it. What temperature change would these rocks undergo if they absorbed 450 kilojoules of heat? So now they're just asking you to find delta T. So looking at Q equals MC delta T, if I'm finding delta T is going to be equal to Q divided by MC. Again, in this case, since I do have the answer in kilojoules, I can use 4 point, oh no, sorry. They gave us 450 kilojoules. So that's going to be 450,000 joules divided by my M, which is 50,000 grams, and my change in temperature is 12 degrees. Oh, sorry. They didn't want temperature. Long day. We need specific heat capacity. My bad. 0.82 joules per gram dot Kelvin. So this is going to be this. Okay. Now I'm back on track. When we do the math, my delta T comes out to be 10.97, or approximately 11 degrees Kelvin. Or Celsius, because we're just reporting the change. Okay, as I mentioned earlier in the introduction, there are two types of calorimetry, constant pressure versus constant volume. In constant pressure, the calorimeter contains a known volume, a solution, and heat lost or gain is prevented by the actual environment of the calorimeter. So therefore, whatever heat is lost is equal to the heat gained. And what we can say is we're going to measure delta H. since delta H is equal to QP, meaning the heat of the pressure. All right, in a constant volume, we are going to measure delta E, since pressure changes. And volume is constant. Okay, so I'm going to go through a couple of examples of each of these, and hopefully that will be helpful. Let's look at a HighTech calorimeter. This is actually a bomb calorimeter, so you have constant pressure. It's usually a metal container of some type, and inside you have what's called a reaction chamber, which is this down here. You can see that there are two electric leads coming out of that, and that is to provide the spark for the actual initial of the igniting of the reactants. And there's like a small crucible within inside the reaction chamber to hold everything. Outside of that is water in the actual container where you see all the blue area. There's a motorized stir that does the stirring for you, and a thermometer to keep track of the temperature changes. And this is the type of calorimeter that you're more familiar with, although we do have some of the metal ones, and we will be doing a lab with calorimetry. In this case, you have a type of container, sometimes styrofoam. You have a cork stopper, a glass stir, and a thermometer. The biggest problem with this is if the material is porous or you're opening and closing the lid, there's always the chance of heat loss to the environment. So let's consider mixing 50 mils of a 1 molar HCl solution with 50 mils of a 1 molar NaOH solution, both at 25 degrees Celsius. Upon mixing, the temperature of the new solution is 31.9 degrees Celsius. So they want to know how much energy is released. We know that this is an exothermic reaction because temperature is increasing. And they want to know how much energy is released in the sample problem on a molar basis. Okay, so perhaps the first thing that is not clear is that they're talking about, we're talking about HCl. When they say how much energy is released in the problem, we're talking about HCl. That's going to help us a little bit later on. So the first thing that we should realize here, even though that it may not be important, is the net ionic equation. Whenever we mix an acid and a base, the net ionic equation is the formation of water. And the only reason why this is important is because the solution is in water. So we know that the heat capacity of water is 4.18. The other thing that we know is that our delta T is going to be 6.9 degrees Celsius. That's the change between 25 and 31.9. And what else do we know? We know that the total volume is 100 milliliters. So V equals 100 mils. Therefore, the total mass is 100 grams. Because 1 mil equals 1 gram. Okay, so I think we can get started here. So we know that delta H equals MC delta T. However, because this is exothermic, I'm going to make this negative, just so we don't forget, because exothermic reactions have a negative delta H. So our mass is 100 grams, our C is 4.18, and our change in temperature is 6.9. And this is going to give us negative 2,884.2 joules, because this cancels and this cancels. All right, so that's the first part of the problem. That's how much energy is released. And then they want to know how much energy is released in the sample on a molar basis. So here's where they needed to specify, really more so, that they were talking about HCl. And I think that's just a typo in their problem, because I did look this up, and another similar problem was written this way, but specifically specified HCl. So how do we do this part? Well, first, we need to figure out how many moles we have of HCl. So for HCl, we have a 1 molar solution, and 50 milliliters is 0.05 liters. So this is going to give us 0.05 moles. We know that the entire problem is releasing negative 2,284.2 joules. So I'm going to put this in kilojoules, so we have negative 2.88 kilojoules. And that's for the entire problem. We're going to divide that by our moles. And we get .57 kilojoules per mole. So in this example, they're talking about the heat of dilution of sulfuric acid. So taking concentrated sulfuric acid and water and producing more diluted sulfuric acid. But when they talk about concentrated, they're talking about starting with 18 molar. So in each of these examples, there's 100 mils of water, and you're starting with 10 mils of sulfuric acid, and then 20, and then 30. And what's happening is that the overall solutions are going to result in a lower energy state. And what that means is they're going to be extremely exothermic. So as you go from sample 1 to sample 3, you are increasing the number of ions in solution. And well, sulfuric acid ions, or the SO4 ions. And what happens is the water molecules, because it's a molecule-ion attraction, try to surround them, and this creates an enormous amount of heat. It's extremely exothermic, and it can even cause it to boil. So as you can see here from sample 1 to sample 3, as I increased the amount of sulfuric acid, the final temperature increased drastically, almost to the point of boiling. So there's two reasons. One, for me, to show you what's happening with the heated dilution here as we increase the moles of a concentrated acid in a solution, but also to reinforce the fact that we never add water to an acid. Adding water to an acid, the water molecules will immediately try to surround the ions, creating an extremely exothermic reaction, almost to the point of boiling, and it could spatter out and give you an acid burn. So we always want to take our water, add a tiny bit of acid to it, stir, make sure the ions are evenly distributed, give a chance for some of that exothermic heat to dissipate, and then add more acid until we get the final dilution that we're looking for. And here you can see the final calculated results of these dilutions. You see the number of moles, and where N is equal to the number of moles of water divided by the moles of H2SO4. And you can also see the resulting heat of reaction. So what this shows us is that the heat of reaction values are dependent on the amount of material present, and that should make sense. Okay, so let's do some examples. A coffee cup calorimeter contains 125 grams of water at 24 degrees Celsius. After 10.5 grams of KBr is added, the temperature becomes 21.1. What is the heat of solution of KBr? And given that no heat is transferred to the surroundings from the calorimeter, and the specific heat of the solution is 4.18. So, a couple of things going on here. We know that this is a constant pressure calorimeter. So heat lost equals heat gained. We also know that Q is equal to, delta H is equal to the Q of the reaction, which in this case is equal to the Q of the solution, because we have liquids. We also know that delta T is 3.1. We know that this is endothermic because temperature is decreasing. We need a balanced reaction, so we've got KBr solid plus H2O liquid yields K plus aqueous plus Br minus aqueous. We also know that we have 10.5 grams of KBr and 125 grams of water. So what's going on here? Q equals MC delta T. We know that our mass of our solution is the 125 plus the 10.5 dissolved in it, so 135.5 grams times the specific heat capacity of water and the change in temperature. So our Celsius cancels, grams cancel, and we are left with 1,800 joules of energy. However, they want specifically, so that's of the whole reaction, they want specifically for the KBr. So we're going to take our 1,800 joules and divide it by 10.5 grams, and that will give us 170 joules per gram for the KBr. Okay, so there was one more thing that I needed to add on to this problem. We calculated that it was 170 joules per gram, but they wanted for the amount of kBr. So the way this question is worded is a little weird. So we need to take into consideration the moles, because joules per gram doesn't give us for the total solution. We need to do it per mole. So 170 joules per gram, and we know that 1 mole of kBr has a mass of 199 grams. And we also know that 1,000 joules is 1 kilojoule. So therefore, that's going to give us 20.2 kilojoules per mole. Normally they'll ask you, I just don't like the way the question is worded. Some of the other examples that we're going to do are a little bit better. Okay, so when 50 mils of 0.1 molar AgNO3 and 50 mils of 0.1 molar HCl are mixed in a constant pressure calorimeter, the temperature of the mixture increases from 22.3 to 23.11. All right, the temperature increase is caused by the following reaction. So a couple of things that we know. We know that this is exothermic because there is an increase in T. Therefore, our delta H has to be negative. And we also know that delta H equals the Q of the reaction, which equals the Q of the solution. I'm not going to write that down. And we know that we have 0.1 molar, 50 mils of both of these. Okay. We know that it's in water, so our C equals 4.18. All right. And we know heat lost equals heat gained. So Q equals, this has got to be negative because it's exothermic. Our total mass is 50 and 50. 100 mils is 100 grams times 4.18 times our change, oh, I forgot to note our change in T is 0.81. Okay. And when we do the math on this, we get negative 338.58 joules. Okay, so we need to know for the reaction. Okay, so what we need to do is we need to go back and look at the number of moles. So we have molarity, which is 0.1 mole, molarity, x over 0.05. Liters is going to give us 0.005 moles. And then we just simply take our kilojoules, negative 338 we can just, 338.58 joules divided by moles, and let's see what we're going to get. I forgot the 8 in there. So that's going to give us, move this up a little, 67716, and that's joules per mole. And this is usually reported in kilojoules per mole, so that would be 67.7. So 67.7 kilojoules per mole would probably be my final answer. All right, bomb calorimetry, typically used to study combustion reactions. Usually we have a hydrocarbon, some oxygen in the bomb, which is the calorimeter containing water. When the reaction takes place, the heat released is absorbed first by the reaction chamber, which is the bomb, where it's taking place. I showed you that in the beginning of the PowerPoint, and then transferred to the surrounding water. It's built to withstand great pressure in a sealed system. So you have it filled with oxygen so that you know that you have enough for combustion to go completely to the end. You have a known amount of water. And then the sample is simply ignited by the electric current that goes down to the chamber. Because we're working with a constant volume, our calculations will lead us to delta E, change in energy. However, because the work done is equal to 0, delta E and delta H are relatively close to one another. So the equation that we're using is the Q of the reaction is equal to negative C in calories, and that's multiplied by your change in temperature. Now, the only thing with a bomb calorimeter is that the kilocals must be determined experimentally using a reaction with a known delta H. So you actually have to run something else first, or already have that data ahead of time. So I'll show you what that looks like. Remember that your C, of course, is your specific heat capacity, and as stated earlier, I'm just reinforcing this, we're measuring delta E rather than delta H because the bomb calorimeter is a constant volume. So we are going to measure delta E, okay? And remember that this is, for all intents and purposes, constant volume. Okay, the combustion of 0.1624 grams of benzoic acid raises the temperature of a calorimeter by 2.71 degrees Celsius. Given that the delta H of combustion for benzoic is negative 26.73 kilojoules per gram, what is the heat capacity of the calorimeter? So this is the answer that you should get, 1.6 kilojoules. Let's see how we get there. First of all, we need to remember that heat lost equals heat gained. We also need to remember that our delta H is going to be equal to negative well, it's usually negative mass C delta T. However, they already gave us the heat of combustion here. So they already gave us this part, which is what we were figuring out before. So it's very easy. In the beginning, we just have to take our grams, 0.1624 grams, and times it by our negative 26.73 kilojoules per gram. And our grams are going to cancel, and then this is going to give us 4.339 kilojoules. However, that's not the answer yet, okay? So that was our heat lost. That was our heat lost, because this negative 26.73 is the amount of heat released in kilojoules per gram. So now we took that and multiplied it by the grams. So basically, we know that for the amount that we started with, we have 4.339 kilojoules. So now what we're going to do is calculate the heat gain. So your heat gained is going to be equal to your kilocalories times delta T. So your 4.339 times 2.71. Oops, sorry, divided by 2.71. Heat gained equals kilocalories times delta T. We know the heat gained. Sorry, let me get this better written here. So 4.339 kilojoules equals kilocal times 2.71. So we divide both sides by 2.71. And we're going to get an answer of 1.6 kilojoules per degree Celsius, which equals our kilocalories, which matches up with that. I need to figure out how to give myself some more room here. Okay, next problem. If 0.2138 grams of vanillin is burned in the calorimeter and the temperature increases by 3.28, what is the heat of combustion per gram and per mole? So they want per gram and per mole, so this is going to be part 1 and part 2. We know that it is exothermic because there's an increase in delta T. I know my mass, and I know that my delta T is 3.28. And there is a typo in this problem that after I tried to work it through several times, that this should be C6, not C8. C6, H8O3, which we're going to need later. Oops, sorry, different problem. My bad, it's the next problem that has a mistake in it. I have too much writing on my paper. Okay. So let's see what's going on. Heat gained. Let's figure out heat gained first. So we can do this very easily. Our heat gained is going to be equal to our kilocalories times our delta T. Okay, so we know in the last problem we used the benzoic as a standard. Remember I said in bomb calorimetry we need a standard. So this was our standard that we just calculated. So that's going to be our 1.6 kilojoules per degree Celsius. divided by our delta T, which is 3.28 degrees Celsius, which is going to give us a total of 5.25 kilojoules. Okay, that's not our answer, okay? We now have to calculate the heat lost, and that's going to be our kilojoules, 5.25 kilojoules, divided by our grams, because they want it in grams, 0.2138 grams, which is going to give us negative 24.56 kilojoules per gram. So that's the first part of the answer, the per gram. Now they want it per mole. So we know we have negative 24.56 kilojoules per gram, and we know that 1 mole of vanillin has a mass of 152.152 grams. So our grams cancel, and our resulting energy is 3736.9 kilojoules per mole. So 3736.9 kilojoules per mole. Okay. 0.1964 grams of quinine is burned in a bomb calorimeter that has a heat capacity of 1.56. The temperature of the calorimeter increases by 3.2. Calculate the heat of combustion. So this is a little bit easier because they gave us a lot of the information that we need. We know that the heat capacity of the calorimeter is 1.56. So very easily my heat gained is going to be equal to 1.56 kilojoules per degree times my increase in temperature, which is 3.2 degrees Celsius, which is going to give me a total heat gained of 4.99 kilojoules. Okay, so that's initially. Now we need to know how much that is per gram. So we're going to take our 4.99 kilojoules and divide it by our 0.1964 grams, and we get a total of 25.41 kilojoules per gram, which is this right here. That's awesome. Now they want to do it by mole. Here's where there's a mistake in the compound. This is C6H4O2. So we have, whoops, sorry, I forgot that was negative because it's exothermic because it increased. And we have negative 25.41 kilojoules per gram, and we know that 1 mole of quinine has a mass of 108 grams. Our grams are going to cancel, and this is going to give us negative 2744.28 kilojoules per mole. Okay, we are not done yet. But we did get a match on this, 2740. They rounded. At Syracuse, I was using exact numbers. Under constant volume conditions, the heat of combustion of glucose is negative 15.57 kilojoules per gram. A 2.5 gram sample is burned, and the temperature increases from 20.55 to 23.25. So right away, I know my delta T is 2.7 degrees Celsius. We need to figure out our heat of combustion. So we've got, we have the heat of combustion, sorry. Using the heat of combustion, 15.57 kilojoules per gram. And we know that we have a 2.5 gram sample. This will give us the total number of kilojoules, 38.93 kilojoules. And now they want to know what is the total heat capacity of this calorimeter if the calorimeter contains 2.7 grams of water. What is the capacity of the dry calorimeter? Okay, so if we take our 38.93 kilojoules and we divide it by our kilograms of water, which is 2.7 kilograms, we are going to get 14.4 kilojoules per kilo. Oops, sorry, not kilograms. Nielsen, Celsius. Jeez. Kilojoules per degree Celsius. Okay. So this is going to be our total heat capacity of the calorimeter. But now they want to know what's the heat capacity of the dry. So the total, right, heat capacity, heat cap, is equal to dry plus wet. So we need to figure out the heat capacity of the water. We have the total, right? This is 14.4. So if we figure out the wet, then we can figure out the dry. So our wet is just going to be from the water. So that's simply going to be our, I'm going to squeeze this in over here, Q equals 2.7 kilograms. I'm going to leave it in kilograms, and .18 per kilogram, and our change in oh no, we don't need a change in temperature here. We just need to calculate that, which is going to be 11.29 kilojoules per degree Celsius. Okay, because our because our kilograms cancel and we're left with kilojoules over degrees Celsius. So this is 11.29, and then when we solve for x, we get 3.11 kilojoules per degree Celsius. Sorry about that. Not enough room to write. Last problem. A 0.5865 gram sample of lactic acid is burned in a calorimeter whose heat capacity is 4.812. The temperature increases from 23.1 to 24.95. Calculate the heat of combustion of lactic acid per gram. So this one's fairly easy. We're not doing that much. So we know that our heat gained is going to be equal to our 4.812. We should have started with this one and ended with the last one. But times our delta T, which is 1.88 degrees Celsius. That's going to give us, and this has got to be negative because it was at least 8.9 kilojoules. And then our heat lost is going to be our negative 8.9 kilojoules divided by our grams, so we get kilojoules per gram is 15.18 kilojoules per gram. And they didn't ask us to calculate moles, but if they did, just to review that, 1518 kilojoules per gram, and we know that 1 mole of lactic acid has a mass of 908 grams, so that's going to give us 1366 kilojoules per mole. But again, they didn't ask us to do that. Just in case you're wondering, lactic acid has a formula of HC3H5O3, because I know that's definitely a burning question on your mind right now. Haha. All right, that's it.